first, okay. Well, first, if any of you have any like questions or anything about the last class or anything else you want to clarify, you can ask them now. Just private chat me. And I would like to mention that in the syllabus, I specifically wrote this course was aimed more towards a middle like AMC 10 level kind of math. So that could be a reason why it may seem challenging to some of you. I feel that if you find this course too hard, don't try to push yourself to actually completely understand everything, as if you probably won't be able to. Just try to focus on little things, and you don't have to retain everything. Just try to retain as much as you can. That is probably the most you get out of this class, at least. So anyway, let's start. And let's see if I can figure out how to disable annotating from other people besides me. Okay. Well, today we're going to be doing polygons, which is just my term for straight geometry, as in geometry that's not focused solely on circles. So yeah, polygon is a shape with only straight edges, and circles and semicircles, or any kind of shape with a curved edge is not a polygon. So we'll start with triangles. They are the most basic polygon. And here is a chart of special points and lines of the triangle. This is not mine, this is from the source. But I would like to detail a little bit about these. The first one is a perpendicular bisector, which is the line that is perpendicular to of a perpendicular bisector of the perpendicular bisectors of a triangle. Yes, my internet is bad. I'm not entirely sure what I can do about it though. Give me. Anyway, is it like a little bit better now, or? Okay, well, okay, as I was saying, the intersection of the perpendicular bisectors of a triangle is just the circumcenter, which basically means that if you described the triangle inside a circle and you took all the perpendicular bisectors of the sides, they'll always, well, look on my diagram, but they will always intersect at one point, and that point is going to be the center of this inscribed circle. And we can actually show this because if we, but anyway, the concept behind this is that for us, the circumcenter is equidistant from every single vertex of the triangle. So when we draw a perpendicular, as seen here, then from the perpendicular bisector theorem, or whatever you, wait, let me rephrase that. Every time you draw a perpendicular bisector, wait, give me a second to have to think about it. We start with a circumcenter and is equidistant to all three vertices. The perpendicular from the circumcenter to each side will bisect the side because we have hypotenuse-leg congruence for a right triangle, where if you have two right triangles, and this only works for right triangles, and we have a hypotenuse and a leg, they all have the same length, then these two triangles are congruent, meaning that all their angles and side lengths are the same. So from that, we can tell that the perpendicular from the circumcenter will bisect the side, and this will apply for each side, and this is why the point of concurrency, which is where they intersect the circumcenter, and it's pretty easy to show that they all go through the same point. So our next special line is the angle bisector, which basically bisects an angle. That's pretty self-explanatory. And this passes through the incenter, or the circle that is drawn inside the triangle. And we can also show this as when we just connect this to the vertices and then drop these radii that are perpendicular since the sides are tangent. We have that these adjacent, like if we look at this section here, we have that these two right triangles are congruent by hypotenuse-like congruence again. So then that means that these two angles are the same, and the line from vertex to the incenter is an angle bisector. The median of a triangle is the intersection of, well, not the intersection, it's just the line from a vertex to a midpoint of a side, here to here. And their intersection is called the centroid. And the special thing about a centroid is that it will always split the median into length of ratio of 2 to 1. Actually, no questions. Anyway, you're oh yeah, so I stopped talking. Okay, I'm not really sure what the person who just messaged me like you're talking about. If you're referring to the angle bisector, then yes, these are congruent, so their angles, so the areas are also the same. But if you're referring to the medians, then yes, we do know that the two triangles created by the medians, they have the same area because they share an equal base and they share the same height. Yes, the one thing you really need to remember about centroid is that it divides the median into 2 to 1. If you're referring to this triangle and all these six triangles, they're not necessarily all the same area. Actually, wait, no, they are. I should probably. Yeah. Okay, you're right. All six of these triangles are the same area, but that's not really too relevant to this point. And lastly, we have the altitudes, which all intersect at the orthocenter. This point is basically not used at all in competition math. You just have to know that it's where all the altitudes meet. There's really nothing special about it except for, yeah. Anyway, I would like to go back to this point about the medians actually, where if we take the intersection of the medians, we'll be left with 6 triangles here. And we can actually show that since we know that these things are in a 2 to 1 ratio, we first know that each set of adjacent small triangles which have an edge on on the same side. For example, if we call this 1 and 2, 3, 4, 5, and 6, 1 and 2 are the same area, 3 and 4 are the same area, 5 and 6 have the same area because they have equal bases and they share the same height. And then we also know that the area of 1 and the area of is half of the area of 5 plus 6 because this base is 1 to 2 ratio from the centroid. So and you can basically from there just derive that 1, 5, and 6 are all the same area, and you can do the same with 2, 3, 4, and eventually you'll find that all 6 are the same area. Anyway, next important thing, angle bisector theorem, which is this, they intersect the incenter. But if there's a theorem with it, it basically states that the side length, as labeled in the diagram at least, when you have an angle bisector, then the ratio of the adjacent side to the segment on the opposing side of the angle, the ratios are going to be like A over B is equal to C over D. Although I think it's easy to remember as A over C is equal to B over D. I won't prove this, but just know that it's true. There is some trigonometry in here that you may not have learned, and it's not actually required for the AMCs. So if any of you are interested in and actually know trigonometry, you can look at the things I put in here, but I won't be covering them in this class, as I'm pretty sure a good amount of you don't know it. So I'll just skip right to Stewart's theorem, which is another cool thing in triangles, where if we take any arbitrary line from a vertex to any side, we'll have that this neat formula right here. If you can't see, I can zoom in. But b squared times m plus c squared times n equals to d squared times a plus m times a times n, where a is the entire bottom side length, and all the other letters are pretty self-explanatory. And an easy way to remember this is man plus dad equals to bum plus sink, or CNC, or whatever. But although this may look complicated and it could be slightly hard to remember, I assure you it's actually very useful when you cannot think of a way to solve a problem and you just want to find a certain side length. So yeah. Well, so now we can move on to quadrilaterals, which are simply four-sided shapes. And when you encounter problems with these, you'll very often see terms that are used to describe these things. Normally they'll use convex, which means that no angle is greater than 180, which means that it's like this or something like that. Where you might see concave, which would mean that there's one angle that's greater than 180, like that. And it's called concave because it caves in. You can please stop annotating, thanks. Even if you're writing okay. Anyway, next we have cyclic, which basically means that it can be inscribed in a circle. As you may not have realized this, but quadrilaterals, not all quadrilaterals can be inscribed into a circle. Only some of them can. For example, we can have quadrilateral like this that's cyclic, and then you can have another one like, I didn't draw that right, but it's very easy to find a quadrilateral that cannot be inscribed into a circle. We can simply just draw like a really, really skinny rhombus or kite or whatever shape that is. And this cannot be inscribed into any kind of circle. Oh, I'm actually getting not fun. Okay, no fun time. Anyway, and then we'll also be talking about parallelograms, which are basically quadrilaterals that are we talk parallelograms, which are quadrilaterals which have two pairs of parallel, hence the name, opposite sides. And within parallelograms, there are a few subcategories that I'd like to talk about. First, we have the rhombus, which has all sides equal, and which means that its diagonals are perpendicular. A rectangle, and rectangle and square you probably already know. And then we have the non-parallelograms. And the important shapes I think that are not parallelograms are trapezoids, which basically only one pair of parallel sides, even if they may not look parallel. And we also have a kite, which basically has two sets of congruent sides, but they're adjacent, and their diagonals are always perpendicular. And this long diagonal right here, the perpendicular bisector of this shorter one. You can prove it using HL again. Anyway, cyclic quadrilaterals are often a key to many problems involving circles, as they're often hidden and you have to look for them. Okay, I think the one special quality about cyclic quadrilaterals that helps you identify them and basically use them is that they're opposite angles. For example, B and D and A and C. when you add them together, it's equal to 180 degrees. And we can actually tell this with the inscribed angle theorem. And please stop annotating. The problem is. Okay, I'm actually getting DDoS right now. Well, not really, but you get the point. Anyway, parallel lines. Oh yes, my co-host, if you can disable annotating, that'd be great. If you can't, sucks, but whatever. Anyway, parallel line interactions. Understanding how parallel lines work are also very important when it comes to simple computational math problems, as a lot of times they'll utilize this to help you solve problems. Where basically, if we have two parallel lines and they're cut by a transversal, as you can see from the figure, we'll have the angles 1, 4, 5, and 8 are equal, and 2, 3, 6, and 7 are equal. Alphademic Learning should be the co-host. Yes. Anyway. But yes, and you can show this is true by using vertical angles, and these are alternate interior. And this is just a theorem about parallel lines. That is very important. I'm using the word important a lot, but it should be so I'd like to move on to other polygons, as this is something you might see. Although I do believe in my challenge problems, it didn't actually really incorporate these too much, although I think I might have shown up. But anyway, the term regular is often used when describing these ones with more sides, as dealing with irregular versions with lots of sides is not fun. So anyway, regular basically means the polygon has every single edge and every single angle are the same value, as in it's equilateral and equiangular. And also the sum of the angles in any shape with n sides is going to be n minus 2 times 180. And you can show this by dissecting the shape into lots of triangles and adding the angles together, which is why we have n minus 2. Anyway, so I've compiled the table of regular shapes that you'll see, generally speaking, and their total angle sum and individual angle values for when they are regular. I don't see the need to just go down the list. You can easily see it here, and it's in your handout. But yes, it's just a table for reference. You don't need to actually know this. It's very easy to just come up with these numbers on the spot using this formula. Using this formula. Okay. Using this formula. Yes. So anyway, the important concept when it comes to these problems is similarity, which basically means that two figures, not just triangles, any kind of shape, they're similar if their corresponding angles are all equal. And this also means that the ratios between the corresponding sides are the same. Yes, going back. I'm not sure what you want me to go back to, but here it is again. If you need to look at it for like 5 more seconds, I'll look at 4 more seconds. All right, moving on. Similarity. Basically, similarity, I was actually on the second point already. The ratio between corresponding sides will stay the same for each figure. The ratio of the areas is the square, the ratio of their side lengths, and the ratio of their volumes, if they are solid, which will cover next week, it's going to be the cube of the ratio of the side lengths. And generally, similarity is used to write proportions, so you can solve for variables. Not entirely sure you'll see similarity problems in here, but I can certainly find some. But I'll give you guys an example. If you have a triangle like this, and they have, let's say this is 60, this is 40, this is 80, and then we have the same thing here, then these two triangles are similar. That means that the ratio between, let's call these sides A, B, and C, and A prime, B prime, C prime, then the ratio like A over C is A prime over C prime, or A over A prime is C over C prime, and any kind of ratios involving two corresponding sides, it's always going to be the same. As long as A always corresponds to A prime in the proportion, and C goes to C prime, B goes to B prime, etc. But yes, knowing how to use similarity is a very powerful tool, will help you a lot. Strategies when you face these kind of problems, always look for right triangles, similar triangles, and sometimes isosceles triangles. Although this is not as important as the other two, because the Pythagorean theorem shows up really, really often for some reason, where you can always just use it when you find a right angle, and it can help you find some side lengths or variable lengths or whatever you need to find. Angle chasing is also another great method where you basically take a complex diagram and just label as many angles as you can with either a variable or in terms of variable or just a number. And maybe you'll find something interesting, like two angles are the same, meaning that the figure is isosceles, or two lines are parallel because their corresponding angles are the same. But yes, if you're out of ideas, angle chasing can be quite useful in certain scenarios. I don't know why I just drew that. But, yeah. And the next strategy is for finding areas of shape that you don't have a very easy formula for. And an example of this is an octagon, a regular octagon at least. There are many ways you can find this area. There are not actually. There are like two ways I can think of off the top of my head. But let me draw it first. We generally take a regular octagon. That looks a lot more regular than this, at least. Oh wait, this is gonna be. Oh, I can't draw here. Stop. Okay, let's take a completely normal octagon drawing, and you can dissect it into something like this, where you have one square, four rectangles, and four isosceles right triangles. And if you know the side length is S, then you can actually find the area of each of these in terms of S. This is not S actually, this is S root 2 over 2. But you get the idea. You can find each of these small areas in terms of S. So that's why I refer to, well, that's what I mean when I say dissecting a big area into smaller areas if you don't know how to do it immediately. Another strategy, this is really general as it varies between problems, is try to get as much information as possible in your diagram. Make it realistic, but don't spend too much time trying to make it look perfect. Try to draw altitudes or other lines that may be important. Usually involve important points. Dropping altitudes is important because you might be able to use the diagram at the end again. So now, actually I missed the point. You have to identify what the problem is asking for and what information you need to be able to find what the problem is asking for. And this is important because it gives you direction. If you're just looking at a diagram and just drawing on it or writing stuff or finding side lengths for literally no reason because you're bored or don't have an idea of how to solve the problem, try to work backwards. Think about what it's asking for and then just derive what you need to get. And maybe if you know what you need to get, you'll be able to find something that you can use. I believe that is actually the last of my lecture, so we can move on to our challenge problems now. If you guys did do these in advance, I will tell you that the first two problems here and here and here, they are a bit harder than the rest of the problems, except for the challenge problem. But yes, if you couldn't do these two, that's totally fine. But so yeah, don't feel bad about it if you didn't get it. Anyway, where was I? I think I'll just do these two harder ones with you guys at least. So first, draw a diagram, and this is actually not a fun diagram to draw because it has so many moving parts in it. So we have a triangle, a right triangle. That's very useful. Pythagorean theorem, you always use it. And then we draw two squares on the side of it. Doesn't look perfect. Like that. And then we know that this is A, this is C, this is B. Maybe it's 12. And I'm going to, I don't actually know. Maybe, this is X, this is Y. And this is W, and this is Z. We know that W, X, Y, and Z are all on the same circle, which we can sort of draw like that. Okay, there are actually a few ways you can do this problem, but I think the easiest way is I actually wrote this at the top. The center of a circle is the intersection of the perpendicular bisectors of all chords in the circle. So it doesn't just apply to an inscribed triangle, because literally for any chord in a circle, the perpendicular from the center to it, it'll always bisect it, and you can prove this using HL congruence as all radii are the same. It just goes off from there. But yeah. And where was I? We were here. Using that, we can actually draw we know that the perpendicular bisector of YX, this is a chord, perpendicular bisector of ZW will intersect at the center of the circle. And it also happens that they will intersect at the midpoint of AB. Now, why do I know this? First off, the perpendicular bisector of a side of a square, it's obviously just going to cut the square in half. So it will pass through the other midpoint of the other side, which is AB. Why is there a whiteboard in the middle of the screen? I have literally no idea. Someone probably put it there, and I can't get rid of it. Actually, I probably can, but I didn't see it. But yes, I did not do that. And we know that this perpendicular bisector is going to be parallel to WB because this is 90 degrees and this is 90 degrees and everything's 90 degrees and it's parallel. Okay, it's a rectangle. So this line, as mentioned before, will pass through the midpoint of AC. But the line parallel to the midpoint of AC is also parallel to the base of BC. It will pass through the midpoint of AB. And if you're not convinced, and you can assume that it does not pass through the same point. However, since it's parallel, this line is parallel to CB, we can show that this small right triangle is similar to ACB, which means that the ratio of side lengths has to be 1 to 2. This is the midpoint. So it has to be the midpoint. That's basically how you can prove it. So we know that the center of the circle that WZYX is on this midpoint. Call this O. Usually you call the center of a circle O for some reason. It looks like okay. Okay, so we know that AB is 12, so these are all 6. And the radius, not radius, but this thing is 12. But what are we actually looking for? We're looking for the perimeter of the triangle, which means that we need to find the side lengths AC and BC. And here is where the variables come in. You can basically let anything be a variable and it will work out. I'll just let WC or AC, but there's this line here, so I don't want to draw it there. We'll let this length be X. So I'm going to say that we can find X with help from the Pythagorean theorem. Okay, if we let this length be X, This length is also x since it's a rectangle. And yes, and if we can also let BC be y, and this length will be y over 2. Okay. So now we can use the Pythagorean theorem on this triangle right here. You see it? Where we basically have, this is radius, and the radius can be found just using the square. This is 12, this is not 12. This is 12, this is 6. You'll be able to find this radius is 6 root 5. But actually, yes, very important. 6 root 5 is the radius. Find using the Pythagorean theorem on this triangle. So after that, we'd have 6 root 5 squared is equal to x over 2 squared plus x plus y over 2 squared. However, we also have that x squared plus y squared is equal to 144 from ABC is a right triangle. So we have two equations and we have two variables, which means that we can actually solve this for both variables. So if we can expand, 180 is equal to x squared over 4 plus x squared plus y squared over 4 plus xy. And we can go about this a few ways. First, I'm just gonna substitute from here. We have y squared equals to 144 minus x squared. So y is just equal to the square root of this, right? So then substituting this, I'm using this a lot. Now, but at this point, this is just going to be a one variable quadratic equation. Basically, what happens from here is that you can just group these like terms together. This is, I'm not entirely sure what it's going to be. But once you have this, it's not hard to find x. As you group this together, you move it to the other side, then you square it again, and then you're left with an equation for x. So that is the plan. Was 180 minus x squared minus 36, as we can combine these like that, is equal to x square root of 144 minus x squared. Okay, well, someone asked why the center is on the hypotenuse of this triangle, and I said that it's because the perpendicular bisector of any chord, which is basically a line segment between 2 points on a circle, it will pass through the center of the circle, and you can prove this using hypotenuse-like congruence. So then we can easily show that the perpendicular bisectors of ZW and XY will intersect at the midpoint of the hypotenuse. Just going back to here though, we have 144 minus x squared plus x times the square root of 144 minus x squared. And this obviously means that x is going to be equal to the square root of 144 minus x squared. So after squaring, you're going to have 2x squared equals 144. So then x is going to be the square root of 72. That's equal to 6 root 2. Since we're actually gone quite far down. Now we know that 6 root 2, this is going to be equal to x, which is AC. And using Pythagorean theorem, we can find that y is also 6 root 2, meaning that this is actually a 45, 90 degree triangle. Quite interesting. There really was no way to find it out without actually doing the math here, though. But all of this means that the perimeter is just going to be 6 root 2 plus 6 root 2 plus 12. And that's equal to 12 plus 12 root 2. That is our answer. Does anyone have any questions about this one? If not, we're moving on. Oh. Anyway, that was actually quite a lot of work. This one, the isosceles right triangle ABC has right angle at C, the area of 12.5, and the raised trisecting the right angle is going to be intersecting the hypotenuse at D and E. It's asking for the area of triangle CDE. This problem, I don't think I'm going to be showing the full solution, but I will give you maybe a little hint, a very big hint actually. Just gonna show how you solve the problem, and I can just leave the algebra for you guys to figure out. So anyway, we have A, B, C, or ACB, and the angle trisector, which basically means that each of these angles is 30. But that's but yes, we won't label that because their diagram is too small for that. Okay, first, since isosceles right triangle, this means that AC equals to AB. And since you know the area is just AC times AB over 2, then this means the side length is 5. Okay. And you can use, this is actually very easy with trigonometry, but we won't use that because it's not necessary. Okay, so first, drop in altitude. That's probably how we're going to find CDE, base times height. And we can drop in altitude right here, and this is actually a very important supporting line. As we can let this length be x, since we know that angle ABC is 45 from the isosceles right triangle part. We know that this is also 45, meaning the small right triangle is also isosceles. So we can quickly label length as x and 5 minus x. And, well, wait, there's more. We know the length of AB is 5 root 2 from the Pythagorean Theorem, as it's also isosceles right, so you can put root 2. So we know that we call this m. Bm is just going to be 5 root 2 over 2. And then from Pythagorean Theorem, we know this length is x root 2. So that means me is 5 root 2 minus x root 2. And we know that cm is going to be 5 root 2 over 2, as MCB is also an isosceles right triangle. So cm is equal to 5 root 2. So now we can set up a Pythagorean theorem thing, I guess you can say, with the length CE, where we have CE squared is equal to x squared plus 5 minus x squared. And this is also, and this is from this small triangle right here, this triangle. I should probably use different colors actually, that would be cool. This triangle. Please stop annotating, thanks. But anyway, we also have another right triangle facing this, with CE is the hypotenuse, and that is CM. And this equals to 5 root 2 over 2 squared plus 5 root 2 minus x root 2 squared. I'm running into my, it's plus 9 root 2 minus x root 2. So now we can just omit CE squared and just have a 1 equation with one variable. And this does not, actually did not write that. But, and yes, if you solve this equation, you will be able to find x. However, we're actually looking for the area of CDE. So once you find x, all you do is you can figure out what ME is from here. And then, CM is 5 root 2 over 2. You just multiply them together. and then you can find the area of CD. Anyway, I won't go over the algebraic expansion, but the area, well, the answer is going to be 50 minus 25. I should not write it in the middle of everything, actually. Yes, the answer is going to be 50 minus 25 root 3 over 2 for any of you who want to perform the calculation and just get some more practice with this algebra. This is going to be the answer if you want to check your work. Anyway, moving on. I think these were the two toughest problems, so the next one should be a little bit quicker. Yeah, please stop annotating. It's sort of annoying. It's sort of annoying. I can handle it a little bit. But anyway, a triangle with side lengths in the ratio 3, 4, 5 is inscribed in the circle. Oh yeah, the question. Okay, I got a question. Are you going to put the recording on Google Classroom? The recordings are actually on YouTube, and I just put the link to the video on Google Classroom. Anyway, so triangle side lengths in the ratio 3, 4, 5 is inscribed in the circle with radius 3. And what is the area of the triangle? All you have to do in this problem is realize that 3, 4, 5 means that the triangle is a right triangle. Yes, it's a right triangle. And this means that the hypotenuse is going to be the diameter of the circle from the inscribed angle theorem. So now we want to find the area of the triangle, and I think you can just do this by finding the ratio. You can, and since you know that the sides are in the ratio of 3, 4, 5, this triangle is going to be similar to a 3, 4, 5 triangle, right? And we know the area of a 3, 4, 5 triangle, this area is going to be 6. And the ratio of the area of two similar triangles is going to be the square of the ratio of their side lengths. This one has a diameter of 6, which means that the ratio of its areas is going to be 6 over 5 squared and times 6. This equals 216 over 25, or 8.64, as it is on the AMC 10 answer thing. But yes, this is the answer. I don't know what that comment was, but I'll let it go for now. Okay, next problem. We do have quite a few problems. I probably won't get to them again, but that's sort of sad. Anyway, next one, we have a cross, and it's 12-sided, and it's not a convex polygon. Anyway, it's a 12-sided polygon, and each of these sides or edges are equal, and they'll have length 4. And we want to find the area of the weird ABCM shape thing. Yes. So then all we're given is that these diagonals, AG and CH, they intersect at M. And all these angles are right angles. Yes, it's stated in the problem. Therefore, it's canon. So first thing we should do is actually connect very properly, at least. Connect these gaps, because it's sort of hard to make triangles when the sides are not complete. Anyway, so what is our plan to find the area of triangle ABCM? Currently, there only seems to be one, which is find the area of this big rectangle and subtract out the areas of the 3 smaller triangles, 1, 2, and 3. Yes, 1, 2, 3. Because there really isn't a great way to find the area of ABCM, as it's not a regular shape, and dissecting it there really isn't a great way to dissect it either. Maybe you could actually extend, and actually one way you could probably extend and cut off that area, but we're not going to do that method. We're going to do this one. So first, since the side lengths are 4, we can know that AH is 12 and CG is 8. and we know the HG is 4. And now here's a cool trick. Since we know that AH and BG are parallel, because ABGH is a rectangle, then angle HAG and angle CGA are equal. You can probably tell from the parallel line interactions that I went over in the beginning. And since we know that these angles are the same and vertical angles are the same, the two triangles AHM and MCG are similar. And what this means is that we can find the heights of AMH and MCG are also in the same proportion as the sides, which is 3 to 2. Using this, we can find this height. I'm not sure what I'm going to call it. I'll just call it H. This height is going to be 3/5 of 4, which is 12 over 5. And the smaller H1, I guess, is going to be 2/5, which is 2/5 of 4, which is 8/5. So from here, we can find the area of the two triangles as 12 over 5 just times 12 over 2. And this is times 8 over 2. And 32 over 5. And 72 over 5. Now we just have to find the area of the triangle HGM. Now to do this, we have to be able to figure out what this height is from M to HG. Now, at first, it may seem like, there really isn't a great way to do this. And you're sort of right, there isn't that great a way to do this, but you can, actually, there actually is a great way to do this. But okay, not right. But you can notice, actually, okay, yes, I'm right. You can notice that if you drop this height, we have a similar triangle right here. From this small right triangle and this larger right triangle. And we know that the ratio between MH and MC is just 3 to 2. So this height is going to be 3/5 of 8, which is 24 over 5. So in the area of this last triangle, is just going to be 24 over 5 times 4 over 2, or 48 over 5. And now the area of the rectangle is 4 times 12, which is 48. So the area of ABCM is going to be 48 minus each of these things. The total of this is 152 over 5, and 48 is just 240 over 5. Yes. So we have 240 over 5 minus 152 over 5. It's going to be 88 over 5, and that's the answer. So yes, key points in the problem. Connect these lines and use similar triangles, and you're basically done. So this is a really great example of how similar triangles are very strong. Very strong way to solve a problem, at least. Anyway, okay. And not enough time. Okay. Next problem. Triangle ABC has AB equals 2 times AC. Let D and E be on. Okay, well, first off, you can realize that it's going to be sort of a weird diagram, and you might have to draw this multiple times as this case right here. So first, you have to realize triangle CFE is equilateral is a very important statement, and also is probably going to be how you're going to be basing your diagram off of. So I'm going to draw the equilateral triangle first. And let's call this C, F, and E. We won't label them for now. So what do we know? D and E are on AB and BC, and F is the intersection of segments AE and CD. So we'll just let this be E, this be F, and we know that A is somewhere on this line, and we also know that A is here, and we also know that B is going to be on this line CE. Yeah, whatever. And then D is just going to be the continuation of CF onto AB. So yes, our diagram looks very cool. And may or not because they're right now the final outcome. But anyway, we have to to know the angle ACB is. Class ends at 2. Yeah. Well, okay. Let me rephrase that. You are free to go at 2 o'clock, but I'll probably end up continuing overtime because I can't calculate my time properly. But yes, I'll probably go overtime. But either way, the video will still be the video of the whole thing is going to be going up, so you won't be missing much if you have to leave. So yeah, that's basically how it's going to work. That's probably not the most responsible thing to do, but yeah. Anyway, so we have AB equals 2 times AC, but we're not given any kind of side length or anything. This suggests that we'll just keep this in mind, but there's really no way to use this for now. That's another thing. If this information is given in a problem, make sure try to use it in some way. Generally, they won't give you red herrings or anything like that. Either what we know is that angle BAE equals to angle ACD. Right? Let's let this angle be x, as we don't really know anything. This means that this angle is 60, and that this angle also 60 from the equilateral triangle part. So then, simple angle chasing is actually how you do this problem. This angle is 60. This supplementary says 120. And this means that this angle is 60 minus x. Here we can find that BAC is just 60 degrees. And we also know the ratio of AB to AC is 2 to 1. So that is actually is enough. Yes. So once we already know 2, 1, and 60 is enough to conclude that this is a 30, 60, 90 right triangle. Now, you might be asking, why is this enough? Maybe it's not 9 degrees here. You may not be asking and drawing random things on an octagon, but that is also your prerogative. So yeah. Anyway, we can show this using congruent triangles or any kind of similar triangle. All we have to do is take an equilateral triangle and cut it in half. And we know this is 2, this is 1, this is 60 degrees. As seen here, we know this triangle is also the same thing. Pretend you don't know the angles just yet. Then we have by side angle side congruence or similarity. It doesn't really matter that these triangles are going to be similar, so they have the same angles. So it must be 90 degrees here. So our answer is just 90. Yeah, that's actually pretty simple. Anyway, moving on. This problem is very. It's really just this really just tests you on whether you know the angle bisector theorem, which is A. It's not A, it's B. A, C, and D. We're given that BD is angle bisector, AD is 3, and CD is 8. And what's the smallest possible perimeter? Please stop drawing. Okay, you're very cool. You can write high. So, anyway, so all you have to do is know that angle bisector theorem AB over BC equals to 3 over 8. And we know that it has integer side lengths. So therefore, the smallest possible value, AB and BC, is just 6 and 16. So we just have 6 plus 16 plus 3 plus 8. That's equal to 33. And we're done. This is sort of a gimmicky problem. Yeah, some problems are like that. They just test if you have certain knowledge points. If you don't know the angle bisector theorem, this is really just a dead end. There's no way to solve it. If you do, you're totally fine. Well, it might seem like I'm rushing, but I sort of am. Okay, so next problem. A dartboard is a regular octagon, and it's divided into regions. And this is actually like the example I showed you earlier. Maybe it's because I saw it. No, okay. Suppose that a dart, when thrown at a board, is equally likely to land in any area, with the probability that it lands in the center square. What this is really asking is you use to find the area of the square over the area of the entire octagon. You can think about this it's really intuitive. It's also something called geometric probability. that we might go over later. I'm not really sure. But it's cool. But yes, area of the square over area of the octagon. So since it doesn't give you a side length, but it's only asking for a ratio, it's okay to just let the side length be 1 or any value. It should not change the answer. And we must know, or we do know, area of the square is just 1 as it's set. Now the trickier part is to find the area of the octagon. I mean, we're already given a dissection, which is nice. And we know this is 1, and in the table it says that the angles of a regular octagon are going to be 135 degrees, and this angle is 90, means it's 45. From that, we know that each of these unknown lengths are just square root 2 over 2. Okay. From here, we can just find the area of each of the 4 squares. It's going to be 4 times square root 2 over 2 squared times 1/2 plus 4 times the areas of rectangles, which is going to be 1 times root 2 over 2 plus 1 for the area of the square. And yes, expanding this, you'll just get root 2 over 2 squared is just 1/2. I'm pretty sure. Yeah, it's 1 plus 2 root 2. I'll expand the problem again. Okay. I'll finish with, just give me a moment. 1 plus 2 root 2 plus 1, which equals to 2 plus 2 root 2. Yes, so our ratio is going to be 1 over 2 plus 2 root 2 is equal to 2 minus 2 root 2. No, I did that wrong. 2 root 2 minus 2 all over 2 root 2 minus 2 all over 4, which is root 2 minus 1 over 2. Okay, now that might have been a bit fast, so I'll just go re-explain this a little bit. The problem itself, I'm assuming you've all read it at least. It wants to find the probability the dart is landing in the center of the square, on the center of the square. And from that, we know that the problem is really asking for the area of the center of the square over the area of the entire octagon, because it's equally likely to land on any point on the board. So then from there, we're already given a dissection of the octagon. We can let the side length be any number, since we're only looking for a ratio. If we let this be a variable s or x, it does not change anything. But using 1 is easy because 1 is a very simple number. So from there, we can find each of these. Well, first, since it's regular, we know that everything is symmetric, which means all of these little lengths are all the same. That's not the only way of showing that they're the same, but I'm just going to go with it. And we also know the angles are 135 degrees from the table I showed earlier. We're given this to the square, so that means this is also 90 degrees, which means that these angles are all 45. So from there, we know the ratio of 45, 45, 90 right triangle is going to be 1, 1, root 2. Since the hypotenuse is 1, we know that each of the legs is going to be 1 divided by the square root of 2, which is the square root of 2 over 2. Then from there, we can find the area of each triangle, rectangle individually, and we find the square and add them all up. And we find the area of the square and divide by the area of the octagon that we have here. And then that's just basically it. And the reason why this 1 over 2 is root 2 is equal to root 2 minus 1 over 2 is because we can rationalize by multiplying by 2 root 2 minus 2 on both sides, which creates different squares in the denominator and makes it an integer and puts the square root on the top. So yeah, it is exactly 2 o'clock. So if anyone wants to go, they can. I'm just gonna go. This is just gonna be a last problem, I think, and then I'll post. I might give you some hints for the challenge problem, and then I'll post the answers for the challenge problem later on in the week. Yes, last problem. In the given circle, the diameter, in the given diagram, the diameter is EB, and we know that this is parallel to CD. We also know that AB is parallel to ED. Angles AEB and ABE are in the ratio of 4 to 5. So what is the angle BCD? Okay, first, since we know EB's diameter, that must mean EAB is 90 degrees. Then from the 45 ratio part, we know that angle AEB is 40, angle ABE is 50, as they add up to 90 and in the ratio of 45, so 40, 50. AB is parallel to ED, so we know that this angle is also 50 degrees. Interesting, isn't it? And since DC and EB are parallel, this must mean that angle EDC is 130 degrees. Now, how do I know this? If we go all the way back up to here, we know that all of these angles, 1, 4, 5, 8, and 2, 3, 6, 7 are equal. We also know that if we add any two of these, for example, 1 and 2 or 1 and 3, etc., it's going to be equal to 180 because they're all supplementary. So that's basically what I'm using here to show that 50, and this must be 130. And now you must be wondering, but now what? BC doesn't really seem like it's connected to anything, and we don't really know what this angle is because we really don't know any of these angles because, well, BC is not parallel to anything, right? And that is actually sort of correct. But then there's also this cool thing where we know that this is a trapezoid, and we also know that if we connect it perpendicular like this, it's going to bisect CD. And what does it tell us? What this means is that this trapezoid EDCB is going to be an isosceles trapezoid. I'll try to But how do you know this? Basically, this is actually a property of an isosceles trapezoid. For one, the only kind of trapezoid that can be inscribed into a circle must be isosceles. So yes, that's one way. And although it might seem like I'm just pointing this out, I didn't tell you this before because I forgot about it. But how do we show this? That any trapezoid that we inscribe in a circle, that can be inscribed in a circle, must be isosceles. Well, actually, we know that it's a cyclic quadrilateral, which means that I'll get back to that. Basically means that opposite angles add up to 180. And we also know these adjacent angles add up to 180 because these two lines are parallel, which means that the two base angles are equal and the two top angles are equal. And we can use this on BCDE. And actually, now that I think about it, this reminds me, there's really no need to do this. All you had to notice was EBCD is a cyclic quadrilateral. This means that the opposite angles add up to 180 degrees, which means that angle BCD is the supplementary to BED, meaning it's equal to 130. So there's actually no need to find EDC, but I just wanted to say that that was one way to do it. But so if any of you were confused, we didn't actually have to do EDC. All you had to show was EDCB is cyclic, so BCD is 130, and that is our answer. However, I did have a question, which was why EDC is 130, and basically, I'm just going to redraw like this, where if the top line be EB, this bottom line is CD, and ED is this transversal right here. And we're basically taking this angle and this angle. And now from the parallel line thing that we had, this angle right here is equal to, not this angle. And since they make a straight line, they must have 180. So EDC is 130. This goes for any trapezoid actually, where we have these adjacent angles, the adjacent base and adjacent whatever this is. These add up to 180, and these two also add up to 180. Yeah, interesting to know. And finally, the challenge problem. This is from 2018. Some of you may have actually seen this when you took it. But yes, our farmer has a really large field in the shape of a right triangle for some reason. And we know that these right triangles' legs are 3 and 4, and he has this corner that is unplanted. And we basically know that the height from this point to the hypotenuse is going to be, this point to the hypotenuse is going to be length 2, and the hypotenuse is of length 5. Yes. So it's asking what fraction of the field is planted, which is basically saying find the area of the shaded region and divide by the area of the white region, not the white region, of the entire triangle. And I'll give you a hint. The way to do this, all you have to do is you basically just want to connect. I'll be drawn. You basically want to connect this vertex. It's the vertices. Please don't take things into your own hands. We don't need vigilantes here. I should be the only authority. Okay. But anyway, why do we connect them? Well, basically we see that these are 90-degree angles right here since it's a square, right? So we just have one. We're just missing hypotenuse, and then we're also missing hypotenuse for this triangle and this triangle. So it makes a lot of sense just to draw lines here so that you have more Pythagorean theorem to work with. And it also says Pythagoras right here. Maybe that's a hint. I don't know. But either way, yes, I did. Either way, so then all you have to do, let a side length of the square be x, and we know this is 4 minus x, and this is 3 minus x. And we know this is 2, right? From here, we can just, there are actually a few ways in this. First way, you can use algebra and express these lengths in terms of, and you can let this be y and 5 minus y, and you can use Pythagorean theorem and express each of these lengths in terms of x and y, and use the two equations you get from that to solve for each x and y. And then once you know all the values, you can find the area because you know all the lengths. But I am pretty sure there is an easier way. And I forgot it was on preparation, 100%. Okay. So basically, the easy way is to notice that you don't really need y, as it's just going to be bothersome to find these areas when you're really only interested in the area of the square. So what we can do is we can express the area of the big triangle in terms of x as it's going to be x squared plus 3 minus x times x over 2 plus 4 minus x times x over 2 plus 5. And we know that this is equal to 6. And how do we know 6 is just 3 times 4 over 2? We're given that it's a right triangle, legs are 3 or 4, so this is 6. And this other way is just by using the fact that we know that the area of the triangle is also equal to the sum of the parts. The whole is equal to the sum of the parts. Yes. Yes, I won't be going further than this, but just know that once you have this equation, you can solve for x, and after that you can find the ratio. So yeah, I'll let you guys work on this challenge problem. and the solution to this will be posted very soon, maybe in a few days on the classroom. So yeah, I think the class is basically over. There's nothing more to cover. If you have any questions, I can stay behind and answer them. I've got time. But if you don't have anything else to do, you can leave. If you want. Okay, question. What topics are you going to talk about in your seminars? I hate to call it that like this, but like I wrote all the topics on the course syllabus, and if you look there, you would probably be able to figure it out. Yeah, any more questions you can keep on asking. I don't have all the time in the world, but I do have a lot of time right now. But yeah. But if not, you can leave. I will be waiting. Yes, okay, so if any of you, oh, someone has a question. Huh. Interesting. Go on. Don't close the meeting just yet. Okay, well, question. Well, the person asking me a question, you are the only person who's asking right now. Is it possible to take an area and find the length of the area spread out? Yeah, I don't really understand, but it's not really possible to. Are you talking about like taking an area and just stretching it out into a line or something? Because you can't do that because an area is made up of an infinite amount of lines, so there's no way. Like you can think about, well, the easy way to think about it is with like a rectangle, where you find an area of rectangle is just like lots of side lengths to stack. Okay, can you talk about your Math Counts Nationals experience? Well, I remember it was actually the 50-year anniversary of the moon landing. So the theme was Moonshot Monday or something. Actually, I have the shirt with me. Oh, I'm not wearing it. So we went down to Orlando, I think, and first day you had some free time to wander around, and we didn't really go to like a big theme park, but it was like a small Disney theme park thing that you could wander around and just spend time with your team. And I find that a lot of times with these like overnight math competitions, a lot of it's a lot more fun. It's a lot more about the fun you have outside of the competition with the people that you're with, and it's probably more of the emphasis of the gathering itself as you're surrounded by other people who are passionate about math. But as a whole, that's the fun side of it. Actually, that was not all the fun side of it. So basically, second day we had all the competition, the competitions and stuff. I didn't do that great actually, but I was like 39th or something. But New Jersey was 8th. I was second on the team. But yeah, after competition, we went to like I actually forget what it was called. It was like the rocket thing. Did I meet Luke? No, Luke is older than me, so he wasn't there. He was not qualified to be there yet. No, he was qualified, but he was in 9th grade or 10th grade. But either way, I'm not in the same age group as him, so I couldn't. But yes, he is still very, very good at math, and I'm not near his level. No problem. Okay, well, I think if no one has any questions,